Hello and welcome to this lesson on relative atomic mass. In today's lesson, we will first understand the concept of isotopes and how their relative abundance determines the relative atomic mass of an element. We will also understand what relative atomic mass is and learn how to calculate relative atomic mass given the relative abundances of isotopes. Through this, we will also understand how isotopes can result in the relative atomic mass not being a whole number. So far, you have learned what isotopes are and explored the concepts of atomic number and mass number. You should already be familiar with how isotopes are atoms of the same element that have different numbers of neutrons, and therefore different mass numbers. Building on this foundation, today's lesson will enhance our understanding by showing how the distinct isotopes of an element contribute to its overall relative atomic mass. By learning to calculate relative atomic mass based on the relative abundances of isotopes, we will see why the relative atomic masses listed on the periodic table are not always whole numbers. Let's dive into the concept of isotopes and how they influence the relative atomic mass of an element. First, let's recap what an isotope is. Isotopes are atoms of the same element that have the same number of protons, but different numbers of neutrons. Because they have the same number of protons, they have the same atomic number and are the same element. However, the different number of neutrons means they have different mass numbers. For instance, chlorine has two common isotopes, chlorine-35 and chlorine-37. Both have 17 protons, but chlorine-35 has 18 neutrons, whereas chlorine-37 has 20 neutrons. The abundance of an isotope refers to how common that isotope is relative to the total amount of the element in nature. The abundance is usually expressed as a percentage. For example, if you have a sample of chlorine, 75% of the atoms might be chlorine-35, and 25% might be chlorine-37. The relative atomic mass of an element is a weighted average that considers the masses of all its naturally occurring isotopes and their relative abundances. We take a weighted average because the different isotopes do not occur in equal amounts. For example, last lesson, we learned that carbon-12 makes up 99% of all naturally occurring carbon in the world. Therefore, even though there are carbon isotopes with greater mass than carbon-12, such as carbon-14, these make up such a small proportion of the carbon in the world that we do not want to count its mass equally. Otherwise, it would skew the average. It's important not to confuse relative atomic mass with mass number. The mass number is the total number of protons and neutrons in an individual atom of an isotope. Relative atomic mass is the weighted average of the mass numbers for all the isotopes of an element, considering their natural abundances. To calculate the relative atomic mass, follow these steps. First, multiply the mass of each isotope by its relative abundance. Then, sum these values for all isotopes. Finally, divide by the total abundance, which is usually 100 if percentages are used. Let's work through an example using chlorine, which has two isotopes, chlorine-35 with an abundance of 75% and chlorine-37 with an abundance of 25%. To find the relative atomic mass of chlorine, first, multiply the mass of each isotope by its relative abundance. 35 times 75 and 37 times 25. Next, we sum these values to get 3,550. Finally, divide by the total abundance, which is 100 in this case. 3,550 divided by 100 equals 35.5. So, the relative atomic mass of chlorine is 35.5. The relative atomic mass is often not a whole number because it's a weighted average. Isotopes with different masses contribute differently based on their relative abundances. As seen with chlorine, the result was 5.5, which reflects the contributions from both chlorine-35 and chlorine-37. In the periodic table you are provided for your exam, the relative atomic mass is displayed at the top of the element. We can see that the chlorine element has 35.5 at the top. Whilst the relative atomic mass of most elements is not a whole number, the periodic table you are provided with rounds the relative atomic mass to a whole number for all elements except chlorine and copper. This is noted at the bottom of the periodic table. Let's dive into some GCSE level questions to apply our understanding of isotopes and how their relative abundance determines the relative atomic mass of an element. Question 1. Given that carbon has two stable isotopes, carbon-12 with an abundance of 98.9% and carbon-13 with an abundance of 1.1%, calculate the relative atomic mass of carbon. First, multiply the mass of each isotope by its relative abundance. For carbon-12, we do 12 times 98.9, which equals 1,186.8. For carbon-13, we do 13 times 1.1, which equals 14.3. Now, we can add these values together. 1,186.8 plus 14.3 equals 1,201.1. Finally, divide this sum by the total relative abundance, which is 100% or simply 100. 1,201.1 divided by 100 equals 12.011. So, the relative atomic mass of carbon is approximately 12.011. Question 2. Chlorine has two common isotopes, chlorine-35 with an abundance of 75% and chlorine-37 with an abundance of 25%. Calculate the relative atomic mass of chlorine. First, we multiply the mass of each isotope by its relative abundance. For chlorine-35, this is 35 times 75, which equals 2,625. For chlorine-37, this is 37 times 25, which equals 925. Now, add these values together. So, 2,625 plus 925 equals 3,550. Now, simply, divide this sum by the total relative abundance, 100. 3,550 divided by 100 equals 35.5. Thus, the relative atomic mass of chlorine is 35.5. Question 3. Why is the relative atomic mass of some elements like copper, which has two main isotopes of copper-63 and copper-65, not a whole number? First, we'll multiply the mass of each isotope by its relative abundance. For copper-63, this is 63 times 69, which equals 4,347. For copper-65, we do 65 times 31, which equals 2,015. Now we add these values together. So 4,347 plus 2,015 equals 6,362. Finally, we divide this sum by the total relative abundance, 100. 6,362 divided by 100 equals 63.62. The relative atomic mass of copper we calculated is 63.62, which is close to the listed value of 63.55. This is not a whole number because it is an average that accounts for the different isotopes and their relative abundances. In today's lesson, we learnt how the relative abundance of isotopes influences the relative atomic mass of an element. The abundance of an isotope refers to how common that isotope is relative to the total amount of the element in nature. The abundance is usually expressed as a percentage. The relative atomic mass of an element is a weighted average that considers the masses of all its naturally occurring isotopes and their relative abundances. It's important not to confuse relative atomic mass with mass number. In order to calculate the relative atomic mass, we multiply the mass of each isotope by its relative abundance. Then we add these values together for all isotopes. Finally, we divide this by the total abundance, which is usually 100 if percentages are used. This explains why the relative atomic mass observed in the periodic table is often not a whole number. It is an average of the masses of an element's isotopes, weighted by their natural abundances, which can include fractional contributions from each isotope. Overall, this lesson has provided a thorough understanding of isotopes, their role in defining the relative atomic mass for each element, and the arithmetic involved in these calculations.